Good afternoon, everyone. Thank you so much for coming. My name is Tania. I will be moderating this series of seminars for the SymbNET Consortium. So briefly introducing Ricardo, he did his undergrad in the Faculty of Sciences in Lisbon, then his PhD in the Medical Faculty of Lisbon also, and currently he's an independent researcher here at IGC with his group focused on technological development of super resolution microscopy, machine learning, and much more, of which for sure he will tell us about. Thank you so much, Ricardo. The floor is yours.
Thank you, Tania. Can you hear me okay, by the way? Okay, I'm going to assume so. And by the way, Nils, pretty cool talk, by the way. Right, so I guess my talk is a little bit of a different pace. I'm going to show you a little bit about the technology we've created in terms of optical imaging, particularly exploiting supersolution imaging and machine learning. And one of the take-home messages I want you to take from my talk is that everything that I'm going to tell you about is easily available to you in the sense that it's inexpensive, a lot of it is computational based, and it should be extremely easy for you to put it to work in your lab if you wish to. And because I have a tendency to overrun my time, I always like to make sure that these acknowledgements come true. So I just want to highlight that everything that I'm going to show you is the work of several people that passed by the lab over the last years, and it's their brainchild at the end of the day. So I'm really thankful to have had excellent scientists working with me. Okay, so I'm going to briefly touch on three things that might be a little bit exciting for this audience. Our work in terms of developing new superposition methods, some of the things that we do regarding spatial and temporal transcriptomics and proteomics, and a little bit of what we do with machine learning also. So to start by telling you a little bit about what we do with supersolutions, I like to take you back a little bit to actually the moment that I decided to become a scientist or an optical physicist. And I'm kind of lucky because I kind of know the experiments that started it all. I was about 15, I was visiting a university, and my older brother actually at the time asked, because he was working on the lab there, he asked me, do you know what happens when you make a laser go through a slit? And at the time, we started putting up the experiment, and I thought, okay, so there's a laser beam, there's some photons, there's an aperture. I think some of those photons are going to come across the aperture. So what I thought was going to happen was this, right? That I was going to get a shorter beam out of it. So we filmed the experiment. And pretty much my slit is going to be those two razor blades that you see there, and we're going to approach them together. And what you're seeing there is pretty cool, because it's exactly the opposite to what I was expecting. You actually, instead of decreasing the size of that beam, you elongate it laterally, and these side lobes start appearing. It's freaking beautiful, and it's amazing. And I couldn't really explain it. It is really against everything that I thought was going to happen. And this little effect was so disruptive to me that I decided to spend pretty much my entire career studying it. So a few years after, when I started looking into studying physics and studying biophysics in particular, I realized that actually everything about microscopy tends to touch the idea of the effect that you saw before, because what you were seeing is actually pure diffraction. It happens that, for example, when you're using fluorescence microscopy, every time you try to look at the point source of light, like a GFP molecule, for example, that light has to go through an objective. That objective, the first thing that it has in front of it is an aperture. And it's an aperture exactly just like the one you saw before, except that now it's actually a circular aperture instead of being a slit. And because it's circular, the effect that you have is, instead of getting that broadening in the single direction, you get an isotropic broadening effect with all the side lobes that you saw before. And that means also that every time that you're trying to look at an individual molecule or multiple molecules, all of them are affected by this diffraction effect. And this actually is at the basis for which you have a resolution limit on a microscope. You won't be able to really resolve individual molecules easily because you have this diffraction effect happening on each individual molecule. To give you a sense of this, think of, for example, a small organelle or a small bacteria. If you try to observe it on the microscope, it's going to get bored because of diffraction. But there are tricks by which we can actually improve resolutions on the microscope and to actually resolve this at a much better scale. And the trick that we often use, and my favorite trick, which is single molecules localization microscopy, is that instead of using conventional fluorophores, we decorate these samples with photo-switching fluorophores. And because these fluorophores are photo-switchable, in a light-mediated manner, I can turn them off, and I can turn on a very small subset. And when I turn on the very small subset, the information that I see here is actually much simpler than if I had all my fluorophores actively emitting. And because it's simpler, I can actually detect and localize each individual molecule that is actively emitting this frame. What do I do after? I turn these molecules off, turn on another smaller subset, detect and localize. And if I cycle through this process of turning molecules off and on, I can detect and localize the vast majority of it. I end up with an estimate of how my sample actually looks like, of the position of those fluorophores, with a much higher resolution than what we could directly observe before, where all the fluorophores would be actively emitting. And this is the basis for techniques like PALM, STORM, FPALM that you might be very well aware of. Okay, but here's the problem, or one of the problems that I tried to solve when I started my lab. So this is the kind of data that we generally acquire for Supersolutions, and this is great data. You see individual molecules turning on and off, which means that we can localize it with very high accuracy. But effectively, what we're doing here is we're spreading information over time to improve our resolution over space. So we're leveraging this dimension. We're losing information in time to get information in space. And this is actually problematic if you now want to go into live cell imaging, because you actually are very limited on the amount of time that you have to actually resolve the sample. On the other side, the amount of illumination that we're putting into these samples, because we're inducing molecules to turn on and off in a light-mediated manner, is incredibly high. We're talking about 1 million-fold more than what you use on a wide field or a Francis microscope. So that's another issue that we have to deal with. And again, if you want to do live cell imaging, the amount of light that you put there is going to have a lot of side effects happening, from the creation of radical oxygen species, which will go on to create metabolic damage on your sample, to inducing apoptotic responses on cells. I guess everyone that has played with a Francis microscope has seen cells dying in 1 million different ways. All right, so how do we deal with this? One way that we dealt with this was mathematically, right? What we wanted to do was to, on one side, use much less illumination, and on the other side, use very few frames acquired in the fast sequence to actually super resolve our sample. And that means that we can image fast and we can image at low illumination. So pretty much we want to extract still Supersolution image from short sequences of images like what you see here on the left. And for this, we create a new mathematical framework to achieve Supersolution, for which we call Supersolution radio fluctuations. And this is broken down into 2 parts. The first part is actually using a special transform, which we call radial fluctuations, in which we try to map points in space which have a high degree of radial symmetry. It happens that if you have a fluorophore that transiently emits brighter than any other fluorophore in its vicinity, it will show the PSA shape. That's diffraction point type shape. And that shape actually has a very interesting feature, which is it's highly radially symmetric. So if we just start asking in space, where do you have points of really high radial symmetry? What you actually get is that you actually start mapping out every time a fluorophore emits brighter than any other fluorophore in its vicinity. And this happens all the time, by the way, because there's no such thing as a perfect fluorophore. All fluorophores oscillate their intensity, and that's because there's instability on their structure, there's collisional quenching with oxygens, there's homo threat happening, there's a lot of features that actually make a fluorophore oscillate. So this is what you get from that transform, but this is actually a little bit error prone also. That's the reason why, for example, even on background, there's a little bit of fluctuations pick up there, and those are actually just pure noise. So we have to get rid of that and recover back structure. One way that we can get rid of it is by the fact that the oscillations that you get on fluorophores actually have correlations to themselves. So fluorophores have a pattern to the way that they oscillate. And this is actually not true for noise. Noise is highly uncorrelated in its own oscillations that you have in time. So that means that if I just start projecting temporal correlations on this data, which is what we do here, what you get back is structure that corresponds to where fluorophores actually exist, where those molecules exist in space, and you dampen down any noise contribution. So what you have now is actually an estimate, a supersolution estimate of the data that you see there on the left. So it's more or less accurately represents the underlying structure that you have. But by the way, I want you to take home that the intensity that you have there actually doesn't mean exactly the same thing. While the intensity that you have here on the image on the left corresponds to the number of photons that were detected on the pixel, and that has some relationship to the underlying stoichiometry of fluorophores that exist in that region of space. What you have here in this intensity is actually the algorithm capacity to detect fluctuations coming from fluorophores on your data. So slightly different messages. All right, and so we built these algorithms, and by the way, over the last years, we've been evolving it a little bit. And one of the things that we just came out with is a new evolution of how it works, which we call enhanced surf. So it's what you see here. And because it is pure mathematics, previously surf was doing a prediction of how the underlying structures should look like, what's the supersolution equivalent of your diffraction limited image. And now we've enhanced a little bit the way that those maths are done to get you more accurate supersolution predictions of your data. And one of the reasons why this actually works much better now is because the new algorithm actually learns from the data. It's a data-driven algorithm on how to self-optimize its own parameters to predict where fluorophores are located in space. So the nice thing is that this is pure maths, right? So it can be applied to most microscopes, most fluorescent microscopes, as long as you obey a few rules. One of the rules is that you need a high NA and high magnification objective, and you need a modern camera for this to work out. But given those conditions, you can apply it to turf, wide field, spinning disk, light sheet microscopy. Most of those methods will be compatible with the maths that we have proposed, and therefore you're able to convert those systems into supersolution systems. Okay, so I told you a little bit about SURF. And SURF was particularly designed for achieving live cell imaging. But can you combine the best of both worlds? Can you combine the best of live cell imaging with the best of fixed cell imaging? And fixed cell imaging is here quite important for us in Supersolution, because if you have a fixed sample, you can take as much time as you want to actually super resolve the location of each individual fluorophore, which is quite beneficial. So you can afford an even better resolution improvement when you're able to do that. So the way that we address this is actually, in a way we've addressed this in an accessible manner, is by developing this system, which is pretty much a simple syringe pump array. And it's built in Lego, by the way, so we like to joke and say that a 14-year-old kid can do it. But this thing that looks like a toy, there's something pretty incredible things. One of the things that it actually does is it replaces most of the bench work you would do when you're trying to fix a sample and stain the sample for fluorescence imaging. So what it means is that using this thing that looks like a toy, we can actually do an entirely automated experiment where we go from live cell imaging to fixed cell imaging. So I'm going to give you here an example, right? These are fully automated experiments. There's no operator running it at hand. The microscope is controlling everything by itself. And what we're going to start doing is we're just going to start by looking at actin on U2OS cell. The cell is nicely fluctuating its actin behavior, as you're going to see. And upon a certain moment in time, we're going to dynamically fix the sample using the syringe pump array. The syringe pump array is going to go through the entire immunostaining protocol, and the microscope is going to finish up by super resolving that same data set upon fixation. So here we go. Turf imaging of actin. I'm going to switch it to surf mode, which allows you a little bit of a resolution improvement. And now what you're seeing is the post-fixation cell exactly after those dynamics that you saw at the beginning. So we get the best of live cell imaging with a last time point where we increase and enhance the resolution that you have on your data. But the cool thing is that now that we went from a live cell to a fixed cell, we can play a few more tricks, because the next thing that I can actually do is with the same syringe pump array, I can do spatial labeling. In this case, I'm using a technique called DNA paint, which allows me to bring in a label and denature that label, take that label off. And again, in a fully automated manner, what I'm going to do is I'm going to label for proteins, strip out that label for different proteins, strip out, label, strip out, label, strip out, label, strip out, which means that I'm actually unlimited, theoretically unlimited on the number of proteins that I can actually map at Supersolution in my cells. Theoretically unlimited. In practice, there are some limitations because there is mechanical stress that we impose into our cells by the liquid exchanges that we need to do for these experiments. All right, so we have a nickname for the system. It's called Pumpy McPumpface. And it's actually quite nice because there's many labs across the world that already have reproduced the system and are happily running them for their experiments. Okay, so I told you a little bit about SURF and how that allows us to do live cell imaging. I told you about Pumpy, how we're then doing sequential labeling and doing live to fixed cell imaging transitions, all that with the benefit of Supersolution imaging. So let me tell you a little bit about what we're doing with machine learning, particularly from the aspect of making it accessible to everyone. So, because I'm quite interested in following temporal dynamics, particularly from the perspective of viral host-pathogen interactions, one of the things that is really important for us is to be able to follow biological behavior for long periods of time. Generally, that means that we're really limited on the light burden we can impose into our cells and the time that we actually have to acquire data. So we have to deal with quite a bit of noise. And it's been quite interesting because machine learning has been quite disruptive in biology in many aspects. My favorite one is actually in denoising data, because currently it beats any other algorithm in the face of the planet. Machine learning algorithms are the best denoising algorithms that exist out there. So for microscopy, that's really amazing. And so we started playing with it a little bit and started extending denoising networks to apply to our microscopy data. And to dive a little bit to that, I'm just going to explain to you a little bit how deep learning works in the context of microscopy. So for you to understand this, let me try to explain how a classical algorithm generally works. On a classical algorithm, what you have is some kind of input data, an image, for example, and then you have a pre-made algorithm that someone has created by taking some characterization of your microscope, taking some parameters from the user, and from there you get a prediction on how the noise image should look like. Now, typically a deep learning algorithm that is being applied for denoising, it does something a little bit different, because what you actually do is instead of having an input image and asking for an output image, you actually have a weakly form algorithm that has no well-defined internal structure yet. And what you do is you show this algorithm examples of input images and examples of output images. So you should already have these images at hand to present to the algorithm. And what you're asking the algorithm to do is through an optimization procedure to learn how to convert the images that you have on the left into the images that you have on the right. So you're giving it two images and you're saying, can you find a mathematical manner by which you translate this type of image into this type of image? So if you present sufficient images to the algorithm, and if you give it enough time to optimize, at some point it will say, I've converged, I find my best capacity, I found a way to convert the image that you have on the left to the image that you have on the right, which means that you now have a trained neural network. And therefore you can present it an input image and you then try to its best capacity to estimate how the noise image looks like. Here's the beauty of it, which is this algorithm knows nothing about the mathematical basis for denoising. It doesn't know what denoising is. The only thing that it knows is that it needs to find some mathematical way to convert the image on the left to the image on the right. So what that means is that the same kind of neural network, I can present it a low resolution image and a high resolution image, and it will try its best to learn how to improve resolution on an image. I can present it an unlabeled image and a labeled image, and we'll try its best to learn how to artificially label those images for you. So there's an amazing number of tasks that a neural network is able to learn to do just by looking at the data and trying to find mathematical ways to translate one type of data into the other type of data. So what have we done here? Oh, and by the way, this is, of course, heavily dependent on the training data that we present to our algorithm, and just to give you a sense of the noisy data set that we use, which is what you're seeing here, is quite massive, and that's a tendency that you have. That you need to present quite a bit of data to neural networks for them to actually be able to generalize well the task that they need to do. So one of the things that we wanted to do was to make some of these analytical tasks more accessible to researchers in life sciences. And there are two limitations here. There's a hardware limitation. You need high performance graphics cards with high performance GPUs to actually do these tasks. These are generally not easily available to most researchers. And you also need to have the know-how on how to do this. So we try to simplify all that by creating a platform called ZeroCost Deep Learning for Microscopy. Here's what it does. For you to be able to use it, the only thing that you actually need is a computer with a browser. And what ZeroCost does is it brokers, and you need some training data and data that you want to analyze. And what ZeroCost does is it brokers communication with Google Drive, and Google Drive is a free service provided by Google, as you know, moving the data there. And effectively, it has a graphical user interface, which is what you interact with, which is based on Jupyter notebooks, but where you actually need no coding skills at all. You have a graphical user interface with buttons, and everything is extremely self-explained to you on what you need to do to run those tasks. So what the ZeroCost does through these graphical user interfaces, it brokers the communication with Google Drive and another service called Google Colab, which is given for free for researchers, also by Google. And Google Colab, pretty much what it does is it provides access to high-performance GPUs that you need to train neural networks and to make predictions with them. That means that through the ZeroCost Deep Learning for Microscopy interface, you're then allowed to do training on a neural network and make predictions with that neural network. After this, you're able to pull your data back and observe the results. So that means that the entire computational framework is taken care of for you. The only thing that you need is some data and a browser, and we do everything on call for you at no cost. So that's what ZeroCost Deep Learning for Microscopy is, right? It's a large ecosystem of image analysis tasks based on neural networks. It's freely available to anyone. It has a really simple user interface. It's designed from scratch for researchers that are not experts in machine learning. And we spent quite a bit of time actually integrating quality control into it so that you know to what degree you can trust the data that you're generating with the platform. To give you a sense of what you can do with it, there's many different tasks from segmentations to supersolution prediction. And I'm just for fun, I'm going to show you some of my favorite ones. So segmentation, it's really interesting. The typical things like nuclear tracking and nuclear segmentations to organelle segmentation. We can also have, for example, semantic segmentation, which means that we're directly identifying cellular phenotypes from the data, which can be super useful for screening, denoising. I'm going to show you some of the crazy ones, which is where things become interesting. For example, this is one of the ones that is a little bit crazy. In this case, what we've done is we implemented a modality translation network. So what we're actually doing is we're training a neural network, showing it bright field images, and also showing it fluorescent images. And what we're asking the neural network to do is to by looking at the bright field images, try to predict how the fluorescence images should look like. Now, this will always have some errors associated with it. But one of the things that you can see, for example, on this bright field image that you have there is there's multiple organelles that you can identify. Some of those organelles are mitochondria. And that's, for example, what the network has learned to do. It has learned to identify what are the mitochondria from the equivalent fluorescence images that you have on that network. Sorry, let me go back to it. There you go. So that's really interesting, because what that means is that the neural networks are learning to filter out information that you can already perceive in really complex images. And of course, for example, one of the things that we're trying to do with this is we're trying to grab data that we have from correlative light EM imaging and try to get, for instance, to educate a neural network on how to identify and drag level structures that you have from EM images. Right. So once we created this, most of the demonstrations that we've done were with eukaryotic cells. We also wanted to demonstrate that these networks could easily be applied to microorganisms, particularly from the perspective of bacteria. And so we recently also come up with a variant of ZeroCost, which is particularly dedicated for microbiology, where we apply most of, or demonstrate application of most of these tasks directly for segmentation, phenotyping, denoising, everything that you might wish for in terms of bioimaging analysis of microorganisms, including, for example, enhancing resolution. In this case, for example, we have a neural network that grabs wide field images and directly predicts how a sim image would look like without us actually spending €500,000 on a microscope that is required to get those supersolution images. So that's kind of an overview of the technologies that I wanted to show to you today. And I am happy to take any questions you might have around it.
Thank you so much, Ricardo. It was a wonderful talk, beautiful images. Questions for Ricardo?
Yeah, I have one, if I may. That was outstanding. Really very nice. This is very exciting. So I understand this concept of trading time for spatial resolution in the high resolution approach. And then you have this trick, but I don't understand how your trick works. This thing about the symmetry of the point sources, which you then do. Because when I looked at the picture you had and saw the pixelation, and you have your light was sort of stringy, right? There's this network that these molecules are lined up in a certain way. They're not random, right? And I was looking at the pixels. I was wondering how you ever find a point source and test whether it's symmetrical in that landscape where there's clearly preferred distributions or directions in the light. I wonder. I just can't understand how it works in practice.
Right. So in those cases, what you're seeing is microtubules, which means that the molecules are aligned in a polymer in this case, right? And pretty much what we are looking at for is gradient convergence. So pretty much wherever you have intensity ramping up in certain directions, and it happens that whenever you have radial symmetry, you have locally all those gradients pointing to the same point, right? And if all those gradients are pointing to the same point vectorially, that means that you have a high degree of radial symmetry. So you must have a radial symmetric object there. Then the question becomes, is that radial symmetric object a molecule, or is it a feature on the data that might have some degree of radial symmetry? We can weight those convergence to a certain size, meaning that we can match it with the size of a PSF to the size that you expect to have from a molecule, which means that you're going to have a higher radial symmetry given those weights for a molecule than most other structures, but there can still be some errors attached to it. That's where the fluctuations come in. So what we do next is, once we start mapping up those degrees of radial symmetry, we know that they should be transient, because fluctuations on full force are also transient. But we also know that there is some K on and K off for the oscillations of those full force. So once we start taking those K ons and K offs for those full force in time, we can use correlations to extract what is likely a true flow for oscillating from noise or any other features that might exist in the data.
Okay. So you still use time to distinguish. In a sense,
yes, we still need to use. We need generally about 100 to 1,000 frames to still be able to distinguish.
It's very fast, so it doesn't move much. That's
very nice. But interestingly, if we have a very fast moving sample, we can't super resolve it at all, because we're still assuming that full force is not moving in space during those short frame bursts that we're acquiring. And if it does, we're not able to pick up sufficient fluctuations to make that prediction accurately.
Thank you.
Pleasure.
Okay, so if anyone else has a question for Ricardo, please feel free to speak with him one-on-one or to email him about it. I just want to thank you again, Ricardo Henriques and Niels Hedeker, for your wonderful talks. These are really, really wonderful seminars. I will just thank you, of course, all of the people that were here. Thank you for coming.